The next topic, I believe maybe you are most interested about this topic. So the Lenslet video coding for dense light field. So actually, let's first talk about the Lenslet video coding, Lenslet video. So it's a generalized representation of a dense light field. Lenslet video might be captured between different kinds of cameras. For example, here. The first part of this slide is the content captured by Planoptic 1 cameras, and the middle part is content captured by Planoptic 2 cameras. These two kinds of cameras, in both of these two kinds of cameras, there are micro lens arrays between the sensor and the main lens, but the settings of the micro lens could be different, so that the micro image could be quite different. So in order to convert such content to, let's say, multiple view images, the conversion could be different. And we need different parameters to describe those different content. But we can also use camera arrays to capture dense light fields content. So not only the Planoptic cameras can be used, but also camera arrays can be used to capture content of dense light fields. So actually, speaking of the requirements, I think maybe you are quite interested about the requirements of the Lenslet video codings for dense light field. There were multiple meetings. We discussed about the use cases and technical requirements for a potential standard together with WG2. So the latest version is N249 from WG2. A draft use cases and the requirements of such an activity. So in that document, the use cases are categorized into two categories. One is the storage and the other one is communication. So let's talk about these two one by one. So for the storage applications, it mostly relates with cameras and also relates with displays. So here are more explanation and provide more evidences about the content provider, the cameras of different types. So as I just mentioned, Planoptic cameras are the major, let's say, major device to be used to generate lenslet content. There are micro lenses between the main lens and the sensor. So that's architecture of the camera makes the special structure of the lenslet image, lenslet video. And for those, these kinds of cameras, the lenslet image may suffer from, let's say, unknown translations and the rotations between those micro lenses. So it is very important to estimate those parameters to understand those sub-picture architectures in the lenslet content. That will be very useful if we want to compress lenslet video content. So as for the compression, we usually need to find out correlations in the lenslet video. There are, of course, temporal correlations between multiple frames of the in the time domain. But in the spatial, the most special thing is the spatial correlation. It might be somewhat different from traditional video. There are spatial correlations, but in that lenslet images, there are angular correlations. So not only the nearby pixels exist correlations, but also some special structure or some kind of different distance pixels, distant pixels might exist in correlations. And for Planoptic 1 captured camera captured content, or Planoptic 2 camera captured content, the spatial or angular or micro image correlation could be different. So that means that when we design the coding tools, we need to consider the structure, the spatial structure, especially the spatial structure in the lenslet image. So I believe this is the most important thing we need to consider for the lenslet video coding. I mentioned the Planoptic camera. Additional to that, there are some special cameras like light field microscopic, which might be used in scientific researches, and those microscopic can capture 3D things like large-scale biological neuron activities with lenslet video. So for those devices, we need to support the compression of large amounts of content. Since there are lenslet arrays, actually the sensor usually have large amount of large volume of data than usual to the video cameras. So that's why for such kind of devices, the compression, even you just need to store the data locally, you need advanced coding technologies for those large amount of data. So that's light field microscopy, and there are also light field endoscopy, which might be used for medicine applications. So the camera with lenslet arrays can be mounted on a bendable cable, and to capture the inner 3D scene of a human body, for example. And for such applications, the storage of large amounts of content is also a technical challenge. So additional to that, in the most recent WG2 and 4 meeting, some information about the application of integrated camera arrays be brought to the meeting, and those camera arrays are used for video surveillance, and it was provided. The information was provided that some airports, for example, in some of our Chinese airports, set up systems with integrated camera arrays to capture content for video surveillance. Those camera arrays can provide a larger field of view and a larger depth of field. So the police can see through occlusions with the assistance of synthetic imaging. And this is a real application. So we believe with such content capture devices, different kinds of capture devices, it is reasonable to establish some standard activities for those special contents. And on the other hand, maybe you will ask, other than the content acquisition devices, we may also need display devices. So here are some analysis about the 3D displays so for Lenslet content. So first kind of such display is the integral 3D display. It's a so the Lenslet array again is used here in such kind of display, and such display can provide the viewer the feeling of 3D dimensional perception as well as 2D motion parallax without wear any glasses. So this is the I think we had one workshop in MPEG in maybe 2018 or 19. NHK demonstrates the such a display in the meeting site on the meeting site. And additional to the integral 3D display, there are also layered 3D display. The structure of the display might be different, somewhat different from the previous type. So there are multiple layer architectures in the display, and the light field of 3D can be recreated by the layered architecture of the display. And again, the 3D three-dimensional perception and 2D motion products can be provided without glass wearing. And additional to that, we have also holographic displays, which can regenerate the light field, 3D light field by computer generated holograms. And so such kind of device displays can avoid the convergence and accommodation conflict for the viewers. So it's more comfortable than the traditional 3D displays. So these kinds of displays need to feed in the Lenslet data. Lenslet data have the advantages of more natural, more fluent of bandwidth compared to other 3D data types. So considering of such constant acquisition devices and display devices, as well as the application in the medical image, we collect the requirements for these different applications. So we need to support different types of representations of dense light fields. So I mentioned there are different types of Lenslet images and videos. And we also need to support different bit depths, color formats. We are not only need to support high efficiency, lossy compression of Lenslet video, but also in some applications, lossless compression might be necessary, might be needed. And additional to the compression of the video data, we also need to transmit information about the architecture of the lenses arrays. So metadata need to be considered in the design of such a standard, and we hope that such a new activity can be based on existing video coding standard such as HEVC or VVC. So extending of existing standard could be considered. So that's for mostly for the storage, for the communication. The most related application could be industry, inspections. I don't think I need to provide more, describe more about this. And there are robotics, especially when we consider the, for example, remote operation, then we need communications of the captured video with Lenslet contents, so that we need to define a standard for communication. So the most important things like complexity, real-time encoding, decoding is an additional requirements for the communication. And that's the application. So then let's take a look at the coding tools. We try to collect in several years of preparation for the real standard projects. So we conducted multiple rounds of exploration experiments to those coding tools. So some coding tools are for PlanOptic 1, some are for PlanOptic 2, some may be useful for both of different kinds of content. And this table provides us information about how good those tools, how many coding improvements, coding efficiency improvement can be brought by those different tools. So the tools such as image reshaping to process those Lenslet content with sub images and micro pixel based intra prediction, as I just mentioned, the special spatial structure in the lenslet image. And there are micro lens based search and some special zooming compensated method. And so these are different tools. And recently, the group also tried to combine some of those tools, which may bring us more than 30% coding gain compared to HVC. And actually, we also conducted some experiments based on VVC. So some for different types of content in different coding configurations or intra or random access and so on. But at this moment, I think the coding gain is still not so many if we consider the actually the screen content coding. It might be useful for lenslet video coding, but the those new coding tools bring us some percentage of coding gains, but it seems still not so sufficient to really start up a new project at this moment. So we are welcome to collect more evidences on new coding tools to see if we can ready to start up a real standardization activity on lenslet video coding.